Next right, applications of keto-enol tautomerism. Applications of keto-enol tautomerism. Applications of keto-enol tautomerism. 1. Conversion of glucose to fructose to mannose or glucose. In biomolecule we have studied, do you remember? Reducing and non-reducing sugar. So what are the non-reducing sugar? The sugars which do not reduce tolerance and failing solution called non-reducing sugar. So example for non-reducing sugar, sucrose and polysaccharides. Okay. Then the reducing property is because of presence of aldehyde group, free aldehyde group. Even though fructose do not contain free aldehyde group, fructose contain keto group. It is a ketohexose. Even though fructose contain keto group, it is a reducing sugar. Why? Then we have very good. Then we have studied in alkaline medium, fructose get converted into either glucose or mannose. Then how this conversion takes place? This we will study. We will study here. Tell me. Let us take fructose. Right now. Fructose is contained keto group on second carbon, third, fourth, fifth, sixth. This is fructose. Okay, this fructose undergo enolization. It is in presence of basic medium. Yesterday class we have studied enolization, acidic medium, basic medium, right? Tell me, in basic medium what happens? Can you tell me? This pi bond shifted on oxygen. Okay. Then what happened? So this, it is an enol form. This hydrogen shifted here. Then what do you get? So it become double bond. O become OH. Then C become CO, and this hydrogen is shifted on oxygen. Come on, tell me. O become what? OH, and the remaining groups are same. Okay. It is a enol. It is a keto form. It is enol form. Okay. Now this enol form, it undergo further reverse like ketone form. It form two products. How? Now, first one is, see here, this sigma electron shifted as a pi bond. Then what it become? It is a C double bond O. Then this pi electron shifted on its carbon. So therefore, now tell me what it become? It becomes negative or not? This carbon become negative, and it become double bond, and this hydrogen shifted on where? Same negative carbon. Okay. Therefore, now tell me, first carbon become aldehyde, second carbon become OH. Second carbon become OH. It may come right side. It may come left side, because now sp2 carbon. No, it's the beginning sp2 carbon. When sp2 carbon converts into sp3 carbon, this OH may go right side, it may go left side. Suppose first carbon is aldehyde group, let it be. Okay, this alcohol group converts into aldehyde. If the second carbon OH comes right side, and third, fourth, fifth is same. it is called glucose. Okay, next, if the second carbon OH goes left side, what it say? Mannose. So in this way, fructose get converts into either glucose or even mannose also. Therefore, these glucose mannose are reducing sugars. That's what fructose can reduce as tolerance and failing solution. So this is we have studied in biomolecule topic. There you have not read this mechanism. Right? This is, it is due to keto-enol tautomerism. Due to keto-enol tautomerism only it gets intermediate enol. This enol further converted into, it may form glucose, it may form mannose. So this is one application. Next, second application is formation of phenol. Formation of phenol. Right. Let us take cyclohexane having 3 double bond, 3 keto groups. Tell me. If there is a 3 keto group, tell me, is it undergo keto-enol tautomerism or not? Yes. Why? Adjacent carbon sp3, no. There are 2 hydrogen, here 2 hydrogen, here also 2 hydrogen. Come and tell me now. What happens? This pi bond shifted on oxygen, then this bond converted to pi bond, and what happened? This hydrogen shifted on oxygen. So therefore, this double bond, C double bond O converts into OH and pi bond will be formed. Like that in 3 molecules, yes or no? So in 3 molecules, the same thing takes place. Okay, it is also in basic medium, nothing but keto-enol tautomerism. What it formed? Of course, derivative of phenol is formed like this. You get 3 OH. It is called a pyrogallal. No, pyrogallal. It is 1, 2, 3, 4, 5. Tell me. 1, 3, 5 trihydroxy benzene. So it is about keto-enol tautomerism. Okay. So in keto-enol tautomerism, again the question mainly depends on which can exhibit keto-enol tautomerism, which cannot exhibit keto-enol tautomerism. And deuterium exchange also we have studied, There was previous question appeared in NEET, deuterium exchange. What is the product obtained? Okay. Next is stereoisomerism. Stereoisomerism. Correct. Stereoisomerism. So isomerism classified into 2 types, one structural and second one is stereo. So structural further classified into 6 types. So we have completed last one, tautomerism, that is a 6th one. So all structural isomerism is completed. Next is stereoisomerism. This is stereoisomerism actually we will study in second PU haloalkane topic, but we will finish here only. Okay. Okay, now tell me. So what are stereoisomers and what is a stereoisomerism? The organic compound which are having same molecular formula but they differ in the spatial arrangement of atoms or a group of atoms in a molecule. So therefore, they differ in what? Only spatial arrangement. Means 3D arrangement, not special. So they differ in the spatial arrangement of atoms or group of atoms in a molecule called stereoisomers, and this phenomenon is called stereoisomerism. Then stereoisomerism further classified into two types. One, conformational isomerism, and second one is configurational isomerism. Okay, conformational and configurational isomerism. Then this conformational isomerism we will study in alkane topic, but anyhow we'll get in alkane topic. I'll finish here only. Next is configurational, we'll get in the second PUC, that is also we'll study here only. Okay, then this configurational further classified into two types. One, geometrical isomerism, which is also called cis trans isomerism, and B, optical isomerism, which is also called enantiomerism. Enantiomerism. Now let's study one by one. First we will finish first configurational, then go for conformational, because we need to understand first this, so that there are some concepts related to this also. So let's see first geometrical, then optical. That will be a stereoisomerism. The organic compounds which are having same molecular formula. The organic compounds which are having same molecular formula, but they differ in spatial arrangement of atoms. Or groups in a molecule called stereoisomers, and this phenomenon is called stereoisomerism. Okay, so take this as this. It is of two types: one, conformational, two, configurational. Configurational further classified into two types: geometrical, it is also called cis trans; optical, it is also called enantiomerism. Okay. Next, right? Geometrical isomerism. Geometrical isomerism. Cis trans isomerism. Tell me. So what is a geometrical isomerism? Cis trans isomerism. See, geometrical isomers are again the organic compound having same molecular formula, but they differ in what? But they differ in the spatial arrangement of atoms or groups around the carbon-carbon double bond. Wait, the difference is the organic compound which are having same molecular formula, but they differ in what? It is a spatial arrangement of atoms or a group of atoms around the carbon-carbon double bond. Then they are called geometrical isomers, and phenomena called geometrical isomerism. Then what is optical isomerism? Optical isomers are also same. They differ in the spatial arrangement of atom or a group of atom around the asymmetric carbon. In optical isomerism, we will study the spatial arrangement of atoms or group of atom around the asymmetrical carbon. Okay, chiral carbon. But here is around the carbon-carbon double bond. Okay, then next is, so the isomers, the organic compound which are having same molecular formula, the organic compounds which are having same molecular formula, but they differ in spatial arrangement of atoms, or group of atoms, or group of atoms around the carbon double bond, called geometrical isomers. And this phenomena called geometrical isomerism. Okay, tell me. Next is, what is the meaning of cis isomer, trans isomer? So what is the cis? Cis isomer is, it is a carbon-carbon double bond, right? In carbon-carbon double bond, if identical groups are same side, like this, AA. If identical groups are same side of the double bond, cis. In isomer, if the identical groups are like AA, it is BB. So if the identical groups are opposite side of the double bond, called trans, right? Cis isomer. The isomer in which identical groups are same side of double bond. The isomer in which identical groups are same side of the double bond, called cis isomer, comma, opposite side of the double bond called trans isomer. Opposite side of the double bond called trans isomer. Next, condition for geometrical isomerism. So what is the condition, or what are the conditions for the geometrical isomerism? Okay. Tell me. Rotation agala. See, there is a cause. I am not asking what is the cause of rotation, cause of the isomerism, geometrical isomerism. What are the conditions? See, it means how to identify geometrical isomerism. In which condition? The first condition is, see, molecule must have either carbon-carbon double bond, comma, or carbon-nitrogen double bond, or nitrogen-nitrogen double bond, or molecule must be cyclic, or even diene, alka-diene, or cumene, means cumulative enes, means polyene, which is called here cumulative double bond. See, in these molecules there is a geometrical isomerism. One, carbon-carbon double bond. Tell me, carbon-carbon double bond means where it comes? Alkene. It means alkene can exhibit geometrical isomerism. Next, second one, carbon double bond nitrogen. It is a oxime. So this double bond is present in oxime, aldoxime, ketoxime. Therefore, oximes can exhibit geometrical isomerism. Then N double bond N. It is a azo compounds, diazo compounds. Next, cyclic compound, that is a cycloalkanes. Next, alka-dienes. Okay, alkenes having two double bonds. Alkynes, they are actually conjugated dienes, and cumulated. What is a cumulated? Cumulated alkenes. It means if there is, what is a conjugated? Double bond, single bond, double bond. It means double bond should be in alternate position, that is a conjugated. If the double bonds are in continuous position, like this, it is called cumulative. Alright? Cumulative alkenes. It is a conjugated alkenes. So in these molecules there is a what? Geometrical isomerism. So you might have studied only alkene, but along with alkene in this molecule it is possible. That is the first condition is this: they must have double bond, carbon carbon double bond, carbon nitrogen double bond, N double bond, cyclic ring, dienes are cumulative double bonds. So in this molecule there is a geometrical isomerism possible. 2. Whether all these molecule can exhibit geometrical isomerism? No. There is another condition. If there is a double bond, each double bonded carbon must have two different groups. That means each double bonded carbon must have two different groups. For example, carbon double bond carbon. So if each double bond has A, it should be B. It is also like AB. That is possible. Next, if carbon carbon double bond, if there is a, it is a B. Something here AC, AB should be different, AC should be different. Or if carbon double bond carbon, if it is A, it should be B. It should be a C, it should be D. It means each double bonded carbon should have two different groups. For example, if it is A is there, it must be different B. Let it be it is A, it is B. Don't say that A. Let it be same or different. But we want each double bonded carbon AB. It means should be different. Like AB, AC, AB, CD. So like that, each double bonded carbon must be attached to two different groups. Then geometrical isomerism is possible. Right? Therefore, in these molecules, geometrical isomerism is possible, and this is the condition. Then what is the cause of geometrical isomerism? Cause of geometrical. Tell me, Atish. So yes, it is a restricted rotation about the around the carbon-carbon double bond. The rotation around the carbon-carbon double bond is restricted. See, for example, I'll take carbon-carbon double bond. Let us take it is a HCH3. Okay, it is a HCH3 which is called cis. Okay, can you tell me cis, is it converts into trans? Is it possible? Let us say in trans is HH opposite, methyl is opposite. No. Then is this conversion is possible? This conversion possible when there is a what? The rotation about the carbon-carbon double bond is possible. So is it carbon-carbon double bond rotation possible or not possible? It is almost impossible. It means, so there is a rotation around the carbon-carbon double bond is restricted. Okay, if it is rotated, you may get this is methyl here, hydrogen here, then this is possible. But the rotation around the carbon-carbon double bond is not possible. Then you may have doubt. Then is it carbon-carbon single bond rotation is possible or not possible? This is possible. Right. The rotation about the carbon-carbon bond is single bond is possible. That's what we will get the what? Conformational isomerism, no? Yes or no? We will study conformational isomerism based on this only. Right? So that is we study separately. There we study where staggered conformation, eclipsed conformation, etc. So those conformations because of carbon-carbon single bond. This carbon-carbon single bond rotation is very easy. It can be rotated. One molecule converted into another molecule. When there is a carbon-carbon double bond, so like if it is molecule having like this bond, two bond, if you try to rotate this carbon, what happens? This carbon, okay, this bond has to broken, no? This bond has to break. If this bond is broken, then you may get this to this. But whether is it energy is what is it? whatever energy required to break this bond, double bond, is available at room temperature? Not possible. That's what at room temperature cis does not convert into trans. Trans does not convert to cis. That's what, which is called restricted rotation at room temperature. The rotation around the carbon-carbon double bond is completely restricted. That's what, cis is completely different, trans is different. There is no interconversion between cis and trans. Okay, therefore, now the reason, the cause of geometrical isomerism is this, the restricted rotation around the carbon-carbon double bond. Okay, so next is, now which following molecule can exhibit geometrical isomerism? That we will study. First write this. Condition for geometrical isomerism. 1. Conditions for geometrical isomerism. 1. Molecules having C double bond C, C double bond N, cyclic ring, comma, alkadienes in bracket conjugated. Q means cumulative double bonds can exhibit geometrical isomerism. Molecule having carbon-carbon double bond, carbon-nitrogen double bond, N double bond N, cyclic ring. Okay. Take this is also. These following molecules can exhibit geometrical isomerism. These following molecules are examples can exhibit geometrical isomerism. Alkenes, oximes, diazo compounds, cycloalkane, alkadiene conjugated, cumulated alkenes, etc. Next, condition 2. Second condition, each double bonded carbon must contain two different groups. Each double bonded carbon must contain two different groups like this: AB, 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 AC, AB, CD. It must be different. Next, cause of geometrical isomerism. Cause of geometrical isomerism. Geometrical isomerism is due to restricted rotation around the carbon-carbon double bond. Restricted rotation around the CC double bond, carbon-carbon double bond. Around the carbon-carbon double bond. Okay. Next one. Geometrical isomerism in alkenes. Geometrical isomerism in alkene. Okay, we will study the geometrical isomerism in all these compounds. Okay, first one is alkene. The following alkene can exhibit geometrical isomerism. The following alkenes can exhibit.
So cyclic ring and double bond.
Which one?
Cyclic
Cyclic ring.
ಅಲ್ಲ ಸರ್ ಅದರ ಡಬಲ್ ಬಾಂಡ್
ಅಲ್ಲ ನೋಡಿ ಕಂಡೀಷನ್ ಅಲ್ಲಿ restricted rotation about the carbon-carbon double bond andre usually alkene. If you take in oxime carbon double bond nitrogen, if you take azo compounds, cyclic ring. In cyclic ring there is a restricted rotation about carbon-carbon single bond, but in cyclic ring. If you take in cycloalkane, it become carbon-carbon single bond only. But if you write carbon-carbon single bond, you write cyclic ring. Okay. Better. Geometrical isomerism in alkene. 1. The following alkenes can exhibit geometrical isomerism. Tell me. A. Let us take carbon-carbon double bond. Can it exhibit AB? AB. Exhibit or not? Exhibit. So to exhibit geometrical isomerism, molecule must have carbon-carbon double bond in alkene. Now each double bond carbon should be attached to different group. If it is A, it should be B. Like here is A, it is a B. Let it be. But two different, no? Next, B. Carbon-carbon double bond. I will take it is a AB. It is a AC. Possible or not? Possible. Next, C. I will take AB. It is a CD. Possible or not? Possible, because AB, we need to see A and B different, C and D different. Next, let us take carbon-carbon double bond. It is a XY. It is a AB. Possible or not? Possible. That means each double bonded carbon should be attached to two different groups. Okay. Next, right. The following alkenes do not exhibit geometrical isomerism. The following alkenes do not exhibit geometrical isomerism. A. Let us take carbon-carbon double bond. It is a AA, AB. Can it exhibit or not? No. Let it be AB, all right. But there is a AA. It should not be. Next, B. Carbon-carbon double bond. It is a XY. It is a XX. Can? No. Do not. So it must be two different groups. Here X and Y. It is XY. It should be X and Y or something different. Do not exhibit geometrical isomerism. Okay. Next example. Example 1. Butene. Butene. Tell me, butene, can it exhibit geometrical isomerism? But, how many carbon? 4. 2ene means double bond on second carbon. So therefore, write the structure. Carbon double bond here, C double bond C. It is nothing but CS3, CS3. There should be a hydrogen. So therefore, you can write this, translate HCS3. It is HCS3. What is this? Cis butene. So what about trans? Carbon-carbon double bond. If two identical groups are opposite side of the double bond, which is called trans. Trans butene. Therefore, butene has two structures: cis butene, trans butene. Both are geometrical isomers. One more example. Malic acid, fumaric acid. So malic acid, fumaric acid also example for cis-trans isomers. Tell me, in malic acid, there is a carbon-carbon double bond. Two carboxyl groups are same side, which is called malic acid. It is a cis. Next, fumaric acid. Two carboxylic groups are opposite side. It is a fumaric acid. The properties of malic acid different, the properties of fumaric acid different. Both are not interconvertible. They cannot be interconvertible. Right? Next, another example. Protanoic acid. CH3, CH double bond, CH, COOH. So will you write cis sign transform? How? See, to identify the cis sign trans, you first identify double bonded carbon. This is double bond carbon. It is another double bond carbon. Tell me, this carbon atom has two different groups, no? Methyl group, hydrogen. This double bond carbon has hydrogen and COH. So will you write cis and trans? Write the cis trans. Next, cinnamic acid. In cinnamic acid, in place of methyl, there is a phenyl. CH double bond CH COOH. So cinnamic acid also exhibit cis trans. Protanoic acid, tell me. CRO. Protanoic acid, cinnamic acid, CI. So write the cis sign transforms of these two. Next, previously CET once question asked that which of the following exhibit geometrical isomerism? Option was this, hex 3-ene. Tell me, is it hex 3-ene can exhibit geometrical isomerism or not? Say, we doesn't know, we have to see. Hex, no, you write hex, how many carbon? 6 carbon. Okay. 6 carbon. Hex 3-ene, right? 1, 2, 3. On third carbon, double bond. Then, here hydrogen will be there, here hydrogen. Tell me, on this carbon, there is a ethyl, methyl. So ethyl, hydrogen, hydrogen, ethyl. Can exhibit or not? Yes. That's it. So here expecting questions are which can exhibit geometrical, which cannot exhibit geometrical. You have to write the structure and identify the answers. So will you write cis and trans for that? It is a carbon-carbon double bond. Okay. On carbon-carbon double bond, one side hydrogen, and this is ethyl. Here also CH2, CH3, ethyl. It is a cis. So what is the name? Cis hex 3-ene. So will you write trans hex 3? Yes. Okay. Next, one more example. 2,3 dichlorobutane can exhibit geometrical isomerism or not? 2,3 dichlorobutane, dichlorobutene. So butene, but is 1, 2, 3, 4. 2, 3 dichlorobutene. Okay, exactly. Butene. 2, 3 dichlorobutene. This. So can it exhibit? Yes. Okay. Third question. Which of the following alkene can exhibit? Which of the following alkene can exhibit? Vasist, can exhibit cis trans isomerism, can exhibit cis trans isomerism. A. Propene. B. Pent-2-ene. 3. pent 1 ene, D 4, but 1 ene, pent 2 ene. So in pent 2 ene there are 5 carbon atom, and on second carbon there is a double bond. Okay, so hydrogen will be there, hydrogen. Therefore, let it be methyl ethyl, hydrogen hydrogen, right? So what is the condition for geometrical isomerism? Double bond should be there, and each double bond carbon should be attached to different group. Methyl hydrogen, hydrogen ethyl. Therefore, it can exhibit geometrical isomerism. Okay, next. If alkene, no, listen. In alkene, if there is a double bond on ending carbon, can it exhibit geometry? If the double bond present on ending carbon or first carbon, so geometrical isomerism is not possible. Right? Very well known. Alkenes having double bond, alkenes having double bond on terminal carbon. Alkenes having double bond on terminal carbon. Terminal in the sense it may be first or last. On terminal carbon do not exhibit geometrical isomerism. Do not exhibit geometrical isomerism. Okay. Next, one more example. Tell me this. Carbon-carbon double bond. There is a hydrogen, chlorine. Here is, it is a fluorine. It is a iodine. Tell me, can it exhibit geometrical isomerism or not? Huh? Then cis or trans are? Trans are?
CIPF rule ಅಂತ ನೋಡಿದ್ರೆ ಕ್ಲೋರಿನ್ ಓದ್ಕೊಡ್ತೀವಿ.
ಓಕೆ.
ಈ ಕಡೆ ಸೈಡ್ ಹೈಡ್ರೋಜನ್ ಗೆ ಎರಡು.
ಓಕೆ ಓಕೆ. ಅದನ್ನ ಕೇಳಿಲ್ಲ. ಸಿಸ್ ಟ್ರಾನ್ಸ್ ಅಷ್ಟೇ. ಸಿಸ್ ಬರುತ್ತೆ. ಓಕೆ. ಸೊ ಸಿಸ್ ಟ್ರಾನ್ಸ್ ಪಾಸಿಬಿಲಿಟಿ ಇಲ್ಲ. We have the similar nomenclature called EZ. Okay, EZ nomenclature. So instead of cis and trans, we go for EZ. But see here, now question is whether it exhibits geometrical isomerism or not. It exhibits geometrical isomerism. To exhibit geometrical isomerism, two conditions: carbon-carbon double bond. There, each double bond has carbon has two different groups: hydrogen, chlorine, fluorine, iodine. Therefore, your answer should be yes. It can exhibit. Then cis or trans are either neither cis neither trans. So that means cis-trans nomenclature is not possible for this. We have another nomenclature called EZ nomenclature that we will do later. Okay? Answer is yes. Okay. Next. So this is how geometrical isomerism in alkenes. Next. Second one. Second one is geometrical isomerism in where? Oxides. Right. Geometrical isomerism in oxide. So oxides are two types: aldoxime and ketoxime. Aldoxime, take them. Ketoxime. And in oxime, what is the bond? There is a N. Okay. C double bond N. Okay. This bond will be there. C double bond N. Okay. Do you remember how do you get aldoxime, ketoxime? Aldehyde reacts with hydroxyl amine. Aldehydes reacts with hydroxyl amine to form aldoxime. Ketones reacts with hydroxyl amine to form ketoxime. Okay. So in aldehyde and ketone topic you will get. For example, let us take CH3 as a general reaction. Okay, R C double bond O. Take down. R C double bond OH aldehyde. It reacts with hydroxylamine NH2OH, which is called hydroxylamine. Tell me, what should be removed? So remove the water molecule. Then R, H will be same, double bond NOH, which is called aldoxine. Aldehyde plus oxine, aldoxine. Okay. Similarly, ketone, C double bond O, it is RR. It is also NH2 reacts with NH2OH reacts. So here also water molecule is removed. What do you get? It is, tell me, double bond NOH, which is called ketoxin. Okay.
R ಎರಡು equal.
R should not be equal. Okay. Then we'll see that. R should not be equal to this R. Means one is R, other should be R dash. Okay. Therefore, aldoxine, ketoxin, these two can exhibit geometrical isomerism. Okay. Now let's see first aldoxine. Tell me, in aldoxine there is a carbon double bond nitrogen, and say there is a OH group and one lone pair will be there. So therefore, listen carefully. Anyhow, this carbon attached to two groups, that is R and H. Then nitrogen attached to what? Nitrogen should be attached to OH. But what is the condition for geometrical isomerism? There must be a double bond. It may be carbon, 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 nitrogen. Double bond is there. And each double bonded atom should be attached to two different groups, R and H. Then what about here is this nitrogen attached to only one OH. But there is a one lone pair also. Okay, one side lone pair will be there, another side OH will be there. Okay, then now tell me, in this case, so we won't use cis and trans. So it is analogous to cis and trans. We use syn and anti. So therefore here, now if H and OH groups, are same side of the double bond, which is called syn aldoxine. Syn aldoxine. What is the condition? Condition is H and OH group should be same side. If H and OH is same side, there is a syn. If it is a H and OH is opposite side. Okay. So let us take it is a H and here R. Now this side is OH and lone pair. Now this is called what? Anti-aldoxine. So syn aldoxine, anti-aldoxine. So but condition is what? It is based on the H and OH group. Okay. So therefore here, write down aldoxine. If H and OH groups, are same side of the double bond, called syn aldoxine, which is analogous to cis, comma, if H and OH groups are opposite side of the double bond, called anti, which is analogous to trans. Analogous means similar to. Okay. It is about in cis trans isomerism, geometrical isomerism in aldoxine. Okay. You can write many examples. For example, you write the cis syn anti for acetaldehyde. Okay, it is acetaldoxime. Acetaldoxime. Will you write? Next, benzaldoxime. Benzaldehyde has oxime. Benzaldoxime. Okay, so write the cis that is syn anti isomers for acetaldoxime and benzaldoxime. Will you write? Next is ketoxime. So what is the cis and trans that is syn anti in ketoxime? Okay, tell me, in ketoxime, what is the syn and anti? Let us take ketoxime. So in ketoxime, there is a carbon double bond nitrogen, OH is there, and there is a R. But in ketoxime, first condition is, if R is not equal to this R, or take R dash, then geometrical isomerism is possible. Yes or no? For example, if these two R are same, can you expect geometrical isomerism?
No.
Geometrical isomerism is not possible. Right? The first condition is what? Each double bonded atom must be attached to two different groups. Therefore, for ketoxime, if R is not equal to R dash, then geometrical isomerism is possible. Geometrical isomerism is possible. If R equal to R dash, geometrical isomerism is not possible. So therefore, now let us see example here. Let me take, it is a CH3 and it is a C6H5, C double bond, N, there is a OH and one side is lone pair. Now tell me, in case of aldoxime, see, in case of aldoxime, what was the condition? If H and OH groups are same side, that is a syn. Like H, OH, same side, syn. H, OH, opposite side, anti. But there is no hydrogen now here. Then how do you write syn and anti? So here syn and anti, it is based on the OH group. OH group. See, this OH group and methyl groups are same. Therefore, it is called syn. Syn methyl. Syn methyl for what methyl? It is methyl, no? Syn for what? Methyl. Therefore, syn methyl and it is a phenyl ketoxime. Ketoxime. Then it is a OH and methyl groups are same side, therefore it is called syn methyl. Methyl group is same side of OH. The meaning of syn methyl. Next, can I write another way? Overall, another name is phenyl group is opposite to OH, no? So therefore, instead of syn methyl, can I write anti-phenyl? Yes or no? That is also correct. Anti-phenyl methyl ketoxide. So both the names are correct. Okay. So therefore, in case of ketoxime, the group which is present same side of the OH group, which is called syn methyl or anti-phenyl ketoxide. Okay. Next, written question: which of the following ketoxide do not exhibit? One question: which of the following ketoxides do not exhibit geometrical isomerism? Which of the following ketoxides do not exhibit do not exhibit geometrical isomerism. Bardira? Tell me. What your question? How? Push here.
So OH is it is opposite to female, so it is anti-female.
Yes.
And above it is methyl,
Aishwarya.
so it is ketoxin.
Liber. Come here. Tell me. If OH group, listen. This OH group is opposite to what? Phenyl, no? Hence it is called anti-phenyl. You know, phenyl is anti-position to OH, no? It is anti-phenyl. No, I have written name. It is a phenyl methyl ketoxime, no? The whole name is ketoxime. It becomes anti-phenyl methyl ketoxime. The whole name is that. Okay? Then, so which of the following ketoxime do not exhibit geometric isomerism? 1. Let us take it is a cyclohexone ketoxime. B. C. Both A and C, A and B. I'll write D here. Tell me, which do not exhibit the geometrical isomerism? A, B, C, D. Both? So A and B. Right? So, ಯಾಕೆ ಅಷ್ಟು ಕಷ್ಟಪಡ್ತಿದ್ದಿಲ್ಲ ಇದು? ಅಲ್ಲ ಬೋರ್ಡ್ ಕಾಣಿಸ್ತಾ ಇಲ್ಲ ಒಂದು. ಸೊ ಆ ಗ್ಯಾಪಲ್ಲಿ ಈ ಗ್ಯಾಪಲ್ಲಿ ಅವ್ರು ಹಿಂಗಂತಾರೆ ಇವ್ರು ಹಿಂಗಂತಾರೆ. ಇಲ್ಲಿ ಬರಲಿ. Okay. So therefore it is a tell me. This is no, it is symmetrical ketoxime, no? Symmetrical ketoxime in the sense this carbon attached to the whole part is same, no? This half part is same, this is also same, no? It's just like, you know, R, which is equals to what? R equal to R dash. Now here also 2 methyl groups are same, both. Now what about this? Okay, this carbon attached to, this is the one part, this is another part, no? Not same. Okay, so therefore it is these two are called symmetrical ketoxime. Write on here. Symmetrical ketoximes do not exhibit geometrical isomerism. Symmetrical ketoximes do not exhibit geometrical isomerism. That is, second one is geometrical isomerism in oximes. Next, third one, geometrical isomerism in where? Diazo compounds. Geometrical isomerism in diazo compounds. Okay, then what are the diazo compounds? N double bond N, there is a R group, here maybe a R dash group will be there. Then each nitrogen has one lone pair. Now tell me, can this compound exhibit geometrical? Yes. To exhibit geometrical isomerism, first condition is what? Double bond. There is a double bond, N double bond N. Second condition is each double bonded atom must be attached to two different groups. Here one group is there, but here one lone pair. Here also one lone pair. Therefore, no, remember one lone pair is always equal to one bond. Right? If the situation comes, one lone pair itself form the one bond. but by donating one lone pair, it forms the one single covalent bond. That's what here one lone pair can be taken as a one covalent bond. That's what we are taking this. Right. Next is, tell me, here also N double bond N, you can write like this, R same side, then lone pair, same side. Is it syn or anti? It is called syn. Lone pair, lone pair delocalized other no today. What may be the possibility? This lone pair may form here, comes here. Then what about this lone pair? Delocalization is possible, but we have to check here is possible or not. Now usually what happened? This lone pair may come here. Okay. Then what happened? This pi electron shifted here, no? That's only possibility, no? If lone pair shifted here, tell me what may be the possibility? R will be as it is, one lone pair. This one lone pair comes extra. Then tell me, this lone pair form the bond, no? Again it become two bond. One bond disappear, one bond appear. Then N, it losing lone pair. Then this. Tell me whether this structure is possible. Not. Why? See, we know that one lone pair equal to one bond, one covalent bond, two bonds, 1, 2, 3, 4, 5. Is it nitrogen valency become 5? No. Nitrogen expand its valency 3 to 4, but not 5. It is anomalous behavior of nitrogen, dinitrogen. That's what this conversion not possible, restricted. Not possible. That's what not. Okay. Therefore, this is a sin. So will you write anti? Same. This is anti. It is a syn diazo. Anti diazo. That's it. Syn and anti. Next, write the syn anti for this. Next, geometrical isomerism in which compounds? Cyclic compounds, right? Cycloalkane. Right. Geometrical isomerism in cycloalkanes. You write it later. Very badala. Syn anti. Geometrical isomerism in cycloalkanes. Let us take. Tell me, cycloalkanes can exhibit geometrical isomerism. Let us take cyclopropane. That is, which cycloalkanes? Disubstituted cycloalkanes. Like for example here, cyclopropane. In cyclopropane, there is a methyl group here, hydrogen here. Here hydrogen, here methyl. So it is a disubstituted, no, dimethyl, 1, 2 di. It means again not 1 dimethyl. So 1, 2, 1, 3, 1, 4, even 1, 5, etc. Disubstituted cycloalkane can exhibit geometrical isomerism. Next point. Then what is the condition or what is the cause of geometrical isomerism? as you told. So there is no carbon-carbon double bond. Actually, geometrical isomerism is because of restricted rotation about carbon-carbon double bond. But there is a carbon-carbon single bond now. Even though there is a carbon-carbon single bond in cycloalkane, the rotation about the carbon-carbon single bond is restricted. Why? So it is just like, you can imagine like this. It is a cyclic ring like triangle. Okay. If all the bonds are strongly bonded here, all three carbons. Now if you try to rotate this one bond, what happens? The whole bond will be broken. If the bond is broken, there is no existence of molecule. Now where is the question of isomerism? That means now here also reason is same. It is due to restricted rotation about the carbon-carbon single bond due to cyclic ring. If there is no cyclic ring, if there is a only open chain like this, carbon-carbon single bond, then this bond can be rotated easily. Okay, it can be rotated 360 degrees. So due to rotation of 360 degrees, you will get a infinite number of isomers. Those isomers are called what? Conformational isomers. The definition of conformational isomerism is that only the isomers which are formed by rotation of carbon-carbon single bond. By rotating carbon-carbon single bond, you will get a many number of isomers. All those isomers are called conformational isomers. That is possible in carbon-carbon single bond. Carbon-carbon double bond not possible. Carbon-carbon single bond in cycloalkane also not possible. Okay, better. Right, geometrical isomerism in cycloalkane. Right, cycloalkanes can exhibit geometrical isomerism due to restricted rotation around the carbon-carbon single bond. Carbon-carbon single bond in cyclic ring. Carbon-carbon single bond in cyclic ring. Next point. The following cycloalkane can exhibit geometrical isomerism. The following cycloalkanes can exhibit geometrical isomerism. Which following? 1, 2 disubstituted, 1, 2 disubstituted cycloalkane, 1, 3 disubstituted, 1, 4. Is it 1, 1 possible? No. 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Not 1, 1 like 2, 2. Right? The following cycloalkane can exhibit geometric isomerism: 1, 2, 1, 3, 1, 4, 1, 5 disubstituted cycloalkanes. Let us take example. Tell me now. Is it cis or trans? Cis or trans?
Cis.
It is a cis. Okay. And it is a cis. Then what is the IPAP name? 1, 2 cis 1, 2 dimethyl cyclopropane. Okay. Then will you write trans? So trans can be written 2 methyl group side, opposite side. Methyl hydrogen. It is methyl hydrogen. This is a trans. Name will be same. It is a cis 1, 2 dimethyl, trans 1, 2 dimethyl. Both are geometrical isomers. But now cis can also be written like this. It is a methyl now. Methyl will be in one plane, hydrogen will be in another plane. Tell me, is it cis or trans?
Cis.
Cis. So thick line indicate it is towards observer. So therefore methyl both are towards observer. Hydrogen away from the observer, it is cis. That means both are equal. Next, trans. So trans can be written methyl hydrogen. It is hydrogen methyl. So this is trans, right? Okay, let's see some example. It is cyclopropane. In cyclobutane, it is chlorine, H. Cis or trans? Cis. Correct? Cis trans. Chlorine, H. Trans. Cyclopentane. Take 1,3. Okay. Methyl, H. You just write cis trans. Cyclopentane. Even cyclopentane, it is 1,2. You can write even 1,3 also. It is bromine, H. Just write cis trans. Cyclopentane. Next, cyclohexane. In cyclohexane also you can write 1,2, 1,3, 1,4. H. Chlorine, H. Write the cis trans isomers. Tell me. Okay, right. In case of, listen, for cyclohexane, one important, take one note. So cyclohexane structure can be written in a Packard conformation. Okay, this is also necessary later. Kelila? Okay. Which is called Packard conformation. In Packard conformation, if there is a, for example, I'll take here 1, 2. 1, 2, it is a methyl cis. Okay, that cis can be written how? Say it is a plane. If I write 1 methyl is above the plane, next it is a plane. Here also above the plane. Right? If the alkyl groups are same side, above the plane, right? So therefore it is also cis. Okay. Now I'll write one more example. We try to identify cis or trans. Let us take, it is a bromine. This is bromine. Cis or trans?
Cis.
Huh?
Cis.
Cis, no? Because you take, this is a plane.
Below the plane.
Below the plane, it is also plane. Below the plane. Therefore, 2 bromines are below the plane, cis. Next, one more. Let us take, it is a methyl group is here, and this is methyl is trans. So it is which substituted? Nitya, Vasishtha. ಹೋಗಿದ್ದೀಯಾ ಮಲ್ಕೊಂಡಿದ್ದಾನೆ ಯಾವಾಗ ಹೋಗಿದ್ದೆ ಅಂದರೆ ಕ್ಲಾಸಲ್ಲಿ ಮಲ್ಗೋದಾಯ್ತು ಎದ್ದೇಳದೆ ಮತ್ತೆ ಆಕ್ಟಿವ್ ಆಯಿತು 1 2 3 4 it is 1, 4 die substituted ತಾನೆ it is above the plane This is below the plane. Therefore, it is so trans. Okay. It is geometrical isomerism in cycloalkanes. Next, geometrical isomerism in dienes, conjugated dienes. భయపడబోకలా fourth one, fifth one. Right. Geometrical isomerism in conjugated dienes. Geometrical isomerism in conjugated dienes. Tell me. So what are the conjugated dienes? There are two double bonds. It must be in conjugated positions, alternate positions. Double bond, single bond, double bond. Okay. Then again tell me condition. What is the condition? One. These, ending carbons, or what is it? Double bonded carbon should be attached to two different groups. Okay. And there may be in here something A, it may be A or B, let it be, no problem. Okay. So therefore, for example, let us take carbon-carbon double bond here. It is a methyl hydrogen. It is hydrogen. It is methyl. Tell me, this is hydrogen. It is hydrogen. Tell me, what about cis trans isomerism? Now, in case of conjugated dienes, there are two molecules. No, this is one part. Okay. This is another part. Now tell me, what about the first part? Cis. Two identical groups are same side. It is a cis. What about this part? Trans. So therefore we should take cis and trans separately, 2 parts. That's it. One more example. Tell me. You all this is right side is cis. This is trans. Okay.